everyone. Today we're going to talk about solving exponential and logarithmic equations. This could be a little bit of a lengthy video, so what I'm going to do is talk you through the notes as opposed to writing the notes as I go. All right, so here is our title, Solving Exponential and Logarithmic Equations. We're going to start with exponential first. Let's look at the property of equality for exponential equations. If I have some base to the power of x, and that's equal to that exact same base to the power of y, that is true if and only if x is equal to y. If and only if means this statement is true going forwards and backwards. So for example, if I have 3 to the power of x equals 3 to the power of 5, then x must be equal to 5. These exponents must be the same because their bases are the same. If x is equal to 5, then I can give them both the same base without changing the value of the equality. So let's solve some equations with exponents in them. Now the easiest thing to do is going to be this type of example here, and there's going to be 3 different examples because there's 3 different ways you might solve these, okay? So in the first example, I have 100 to the power of x equals 1 over 10 to the power of x minus 3. Notice the x is in the exponent. If at all possible, what you would like to do is write your equation with the same base on both sides. So I can write 100 with a base of 10. That would be 10 squared, in this case, 10 to the 2x. I can also write 1 over 10 with a base of 10. 1 over 10 is 10 to the power of negative 1. Now we know with the power to a power property of exponents that what I can do is distribute this negative 1 with multiplication. So that's the same thing as 10 to the negative x plus 3. Now that I have the same base, I can set the exponents equal to each other. That means that 2x must be equal to negative x plus 3. From here I would solve, so I'd add x to both sides, get 3x equals 3, divide both sides by 3, and find that x is 1. It's really important that you check these. There are a lot of extraneous solutions. So that would be 100 to the power of 1 equals 1 over 10 to the 1 minus 3. I've just taken x from my original and I've substituted in a 1. 100 to the power of 1 is 100. 1 over 10 to the power of 1 minus 3 is to the negative 2. 1 over 10 to the negative, that means I take the reciprocal. That gives me 10 squared. 10 squared is 100. Both sides are equal, therefore my solution is true. The next way you'll see this is you will actually just see an exponent. So let's say I have 2 to the power of x equals 7. There's no way that I can rewrite 7 with a base of 2. So 2 to any power is always an even number. 7 is not even. So I can't get these to have the same base. Since they cannot have the same base, the first thing I'm going to do is write these as a logarithm. So I'm going to rewrite this exponent as a logarithm. It's now log base 2 of 7 is equal to x. Log base 2 of 7 is an irrational number. So I'm not going to write out that decimal. I'm just going to leave it as is so that it's in its most exact form. When I check this, the exponent now is log base 2 of 7. So I have 2 to the power of log base 2 of 7 is equal to 7. And we know from the inverse property of logarithms that when you have the same base in your logarithm and in your actual base, that these two bases essentially cancel each other out and you're left with just the argument. So 7 equals 7. In the event that your exponent, being where your variable is not isolated, you're going to want to isolate that term with the x first. So notice my x is in the exponent for e, so I need to isolate e to the power of negative 0.3x. I'm going to do that by adding 7 to both sides, and then I'm going to divide both sides by 4. So I'm left with e to the negative 0.3x is equal to 5. Now that the term with the x is isolated, I will rewrite this as a logarithm. I'm going to choose natural log, right, because e is my base. So if e is my base, I'm going to go natural log. The natural log of 5 is equal to the exponent, negative 0.3x. Remember, I'm trying to find x, not negative 0.3x, so I'll divide both sides by negative 0.3. Now that x is isolated, this would be my solution. This is also an irrational number, so I'm not going to put that in my calculator and get an unending, unrepeating decimal. I'm just going to leave it as is so it's in its most exact form. To check this, I just take this fraction here and I put it in place of x in the problem. Negative 0.3 times a fraction with negative 0.3 in the denominator will cancel those out. So I have 4 times e to the power of the natural log of 5. E to the natural log of 5 is equal to 5. We know that from the inverse property of logarithms. 4 times 5 is 20. 20 minus 7 is 13, and this is equal on both sides. Let's talk about logarithms. So the property of equality for logarithmic functions is log base b of x is equal to log base b of y if and only if x is equal to y. So remember, if and only if means this statement is true going forwards and going backwards. So as an example, if log base 2 of x is equal to log base 2 of 7, because these logarithms have the same base, that would mean that x must be equal to 7. So the arguments must be equal. If x is equal to 7, then I can take log base 2 of both sides and maintain that equality. Let's solve some equations with logarithms. Again, you'll see this about 3 different ways, so let's go over the 3 different ways you'll see this equation. First, I notice that I have a natural log equaling another natural log. Because these logarithms have the same base, their arguments are equal. So that means that 4x minus 7 is equal to x plus 5. Then I would go ahead and solve by subtracting x from both sides. Then I would add 7 to both sides and divide both sides by 3, and I'm left with x equals 4. When I plug that 4 back into the original, I end up with natural log of 16 minus 7, or the natural log of 9, which is some irrational number. This side also simplifies to the natural log of 9, and whatever irrational number that is, the natural log of 9 will be equal to the natural log of 9. You will also see just a logarithm on one side. If you only have a logarithm on one side, what you can do is you can immediately go ahead and rewrite that as an exponent. So I'm just going to take this logarithm and rewrite it as an exponent. 2 to the power of 3 equals 5x minus 17. 2 to the power of 3 is 8. And then from there, I would just solve like a basic 2-step equation all the way to where x equals 5. I'll plug that answer back in to check. And I end up with log base 2 of 25 minus 17, which is log base 2 of 8. Remember what it means to be a logarithm. So that means 2 to some power should be equal to 8, and 3 is that power. So log base 2 of 8 is equal to 3. Now, in the event that there's more than one logarithm and both logarithms are on the same side, here's what we're going to do. We're going to condense this down to logarithm so we can follow the steps from the previous problem. So this is addition. Remember, addition of logarithms means you can multiply the arguments. So that means that this is the same thing as log base 10 of 2x times x minus 5 equals 2. And then I'm just going to distribute that 2x. Now that I've written this whole thing as a single logarithm, I'm going to rewrite that as an exponent. Remember, your common log, the base is 10. So 10 to the power of 2 is equal to the argument. And then from there, I'm just going to solve. This is a quadratic because I have x squared. 10 to the power of 2 is 100. Let me set all of that equal to 0. Once that is equal to 0, I'm going to go ahead and fully factor that. That is fully factored at x equals 2 times x plus 5 times x minus 10. Zero product property tells me that either 0 is equal to 2, which of course is not true, or x plus 5 is equal to 0, or x minus 10 is equal to 0, which gives me negative 5 as a solution and 10 as a solution. Really important that you check these. We're going to see that negative 5 doesn't work. So here I'm just going to look at 10 first because it does work. So I substituted in 10 for x. Remember, 2 times 10 is 20. 10 minus 5 is 5. Now here, addition, I know that addition means I can multiply these arguments. 20 times 5 is 100. The log of 100 is equal to 2. Now, when I substitute in a negative 5, I end up with the log of negative 10. The log of negative 10 is undefined. Your argument cannot be negative. Because, remember, to be a logarithm, I'm saying 10 to some power is equal to negative 10. There is no exponent in the world that turns a positive number into a negative number. So this is not possible. Okay, which means this answer is undefined, and negative 5 is what we refer to as an extraneous solution, meaning your solving steps were correct, but that solution does not work. And that's the basics of solving exponential and logarithmic.